11 மணிக்கு வர்றேன் அப்படிங்கிறாங்க மேடம், கிளம்புறாங்க. நான் சொன்னேன், நேற்று இஸ்காவுக்கு பாலசம்சர் வந்திருந்தாரு, முருகன் சொன்னேன் சார் 10:05க்கு நான் வந்துடுறேன்னு சொன்னேன். அது கவிதாசி ஃபோன் பண்ணிட்டு 11 மணிக்கு நான் வர்றேங்க சார், நீங்கள் மேத்ஸ் முடிச்சு வாங்க அப்படிங்கிறாரு. ஃபிசிக்ஸ் அதனால் நான் ஒன்று பண்ண அதை நான் அதை முடிச்சுட்டு வந்துட்டுலாம் ஃபிசிக்ஸுங்க இந்த மேத்ஸ் முடிச்சுட்டு வர்றேன், இந்த தமிழ் முடிச்சுட்டு வந்துடுறேன். இப்போ நான் இந்த மேத்ஸ் கூட இப்போ அட்டன் பண்ண முடிய சூழ்நிலைங்க.
A pleasant morning to one and all. Talent wins games, but teamwork and intelligence wins championship. I'm L. Vidyarani.
And I'm N. Mohanapriya. It's a pleasure to host this international virtual conference on mathematical and computational models.
Collaboration in academics helps to enhance the quality of education. We are very fortunate to have such collaboration between Kongunadu Arts and Science College, Coimbatore, and Bannari Amman Institute of Technology, Satyamangalam, which in turn has brought up this international conference into reality.
Conference is a group of intelligent people gathered together to share the knowledge. Happy to have all such intelligent people gathered here, having their ears open to fill the thirst of knowledge and having their minds open to stimulate the budding researchers. We appreciate you all for taking time off your busy schedules and joining with us today. We hope this conference will bridge the gap between the thirst of knowledge we have lined up for you to be a fruitful and engaging. One song can change a moment. One idea can change a world. One step can start a journey, but a prayer can change even the impossible into possible. Now, I invite
श्रीचक्रराज सिंहासनेश्वरी श्रीललित श्रीचक्रराज सिंहासनेश्वरी श्रीललिताम्बिकये भुवनेश्वरी आगमवेदकलामयरूपिणी अखिल चराचर जननी नारायणी नागकङ्गन नटराज मनोहरी ज्ञानविद्येश्वरी राजराजेश्वरी श्रीचक्रराज सिंहासनेश्वरी श्रीललिताम्बिकये
Thank you, Deepika, for your mesmerizing voice. Welcome with sweet and gracious speech will create magic for today's morning. I would like to invite Dr. P. Saravanamurthy, Mathematics, Bannari Amman Institute of Technology, to welcome the gathering. Sir?
Yes, ma'am. Thank you. Good morning to all of you. Thank you in advance in joining with us at this two-day international conference. It is our pleasure to conduct this conference with Kongunadu Arts and Science College, Coimbatore. Both the institutions have a vast experience in research and academics. We excel in engineering and technology, and Kongunadu Arts and Science College excel in arts and science stream. We celebrated in the year 2020 the Silver Jubilee year. Our aim is to bring all mathematicians and researchers in a forum. They will share their ideas in applied and pure mathematics. That is actually the motive of this conference. We have around 720 registrations. Around 720 registrations. Out of this, we selected 220 as the presenter. And among this, 67 are from outside India. The other countries like Algeria, Bangladesh, Cambodia, Egypt, Lebanon, Nigeria, South Africa, Philippines, etc. So it is our great pleasure to conduct this. In this moment, I welcome all participants from India and outside India also. I welcome the principals of Bannari Institute of Technology and Kongunadu Arts and Science College, Coimbatore. And I welcome the faculty members of BIT and Kongunadu Arts and Science College. And I welcome the students of both the institutions. And I welcome the participants. Thank you. Thank you all.
Thank you, sir, for your warm welcome.
Research is a single root of a tree which grows in different branches of knowledge. Conference plays a vital role to strengthen this root. Now I invite Dr. M. Vigneshwaran, Assistant Professor of Mathematics, Kongunadu Arts and Science College, to present the theme of the conference. Sir?
Very good morning to all present here. Last year, an MOU has been signed between Kongunadu Arts and Science College, Coimbatore and Bannari Institute of Technology. The researchers from the Department of Mathematics in both the colleges have planned to undergo collaborative research works. As an outcome of this MOU, this conference has been jointly organized to enhance the quality of research. The International Virtual Conference on Mathematics and Computational Model provides a global platform for academicians, researchers, and students to gain the knowledge in the recent trends in the fields of mathematics, computer science, engineering, and technology. Eminent persons from abroad who are excelling in their fields of specialization are research persons who share their ideas and knowledge. Dr. ADEM KILICIMAN from Malaysia will deliver a talk on some applications on generalized functions and singular operations. Dr. Inauguration from Turkey is going to deliver a talk on some applications of Riemannian geometry in deep learning. Dr. Sana Kadora from United Arab Emirates will deliver a talk on generative adversarial networks and its applications. Dr. Subino from Indonesia will deliver a talk on computing max plus algebra and its applications. Dr. Salaban from Poland is going to deliver a talk on decision support systems using fuzzy logic. Professor Jaroslav is going to deliver a talk on MCDA methods in sustainability domain, recent developments and challenges. Professor Mohammad Sajjad is from Saudi Arabia is going to deliver a talk on fractals. It is an international forum for researchers and students to have interaction with the eminent speakers and experts to debate the foremost recent innovations and findings in the fields of mathematics, engineering, and technology. This conference also helps the researchers to share and exchange their knowledge, work experiences through paper presentations, and the high quality research papers in the areas of mathematics, computer science, engineering, and technology will be published in Corpus Index journals and peer-reviewed journals. This conference has united around 720 academicians and researchers, out of which 65 are foreign delegates from Algeria, Bangladesh, Cambodia, Egypt, Lebanon, Morocco, Nigeria, Pakistan, Saudi Arabia, and South Africa. Around 280 research articles were received and 220 research articles were accepted for presentations. 23 parallel sessions have been arranged for paper presentation. An abstract is published consist of the proceedings of the conference and the abstract of the submitted papers. Hope this conference will meet all your needs. Thank you for giving the opportunity. Thank you.
Thank you, sir. Gratitude makes sense of our past, brings peace for today, and creates a vision for tomorrow. Now, I invite Dr. D. Vijayalakshmi, Assistant Professor of Mathematics, Kongunadu Arts and Science College, to propose the vote of thanks. Ma'am, please.
Thank you, Priya. A small cheer and a great thanks makes a good evening. A very good morning to one and all present here. It is my honor and privilege to propose the vote of thanks for this occasion on behalf of IDEM CM 21 to all the distinguished guests of this inaugural function for grading their importance and sharing their findings and opinions today. It's my great privilege to submit my sincere thanks and gratitude to our Honorable President, Dr. M. Arujami sir, and our most respected Secretary and Director of our college, Convener KASC Coimbatore Chapter, and Syndicate Member of Bharatiya University, Dr. C. A. Basiji Madam, for constant support and encouragement. Thank you, ma'am and sir. Alone can do so little. Together, we can do so much. I express my profound and sincere thanks to the most respected Principal Dr. C. Palanisamy and Dr. K. Shivakumar, Dean, and Dr. S. Jagadishwaran, Dean Academics of Bannari Institute of Technology. Sir, thank you for a wonderful opportunity to conduct this conference in collaboration with our institution. I extend my sincere thanks to respected Head, Department of Mathematics of Bannari Institute of Technology, Dr. P. Saranamurthy sir, for delivering wonderful welcome address. Thank you, sir. I thank my friend Vigneshwaran for presenting the theme of the conference in brief. Thank you, Vignesh. Collaboration is about compassion, love, support, kindness, and the power that we gain when we share with each other and lean on each other. I offer my sincere thanks to the conveners and organizing secretaries of this conference of both the colleges. Thank you all for wonderful initiative and effort. I submit my sincere thanks and gratitude to each and every participant for attending this session and making a grand success. Thank you all.
Thank you, madam, for your nice gratitude. The secret to getting ahead is getting started. Every moment is a fresh beginning. Now we are on to the technical session of this conference. To be the first, I would like to invite Dr. L. Vidyarani, Assistant Professor of Mathematics, Kongunadu Arts and Science College, to introduce our first keynote speaker, Dr. Adam Kilman.
Thank you for giving me the opportunity to introduce the first keynote speaker. I'm delighted to take this opportunity to introduce the chief guest of the first technical session. We have an eminent professor, Dr. Adam KILICIMAN from University Putra, Malaysia, who is going to deliver on the topic some applications of generalized functions and singular operations. He has completed UG and PG in Hasteb University, Turkey, and has completed his PhD in University of Leicester, UK. He has acted as a reviewer in many reputed journals like American Mathematical Society, Computing Reviews, and Zentralblatt. He is having an academic experience of 24 years and is currently working in University Putra, Malaysia. He received many academic and non-academic awards. He has published around 400 research articles in scientific peer-reviewed journals. He has also published 6 books and 3 book chapters. He has completed 16 research projects, which is really a miracle, and 9 ongoing projects. He is having 6,000 Google Scholar citations and more than 2,000 Scopus citations. We are very proud to have such an eminent person as the first keynote speaker. Sir, over to you. Share your knowledges where we have our minds open to get words from you. Sir, over to you. Adam KILICIMAN, sir.
Thank you very much for nice introduction. Hello, everyone. Please allow me just upload my file first of all. Then I will start my presentation. Just a moment, please. Can you allow me to upload? Seems cannot. Yeah, okay, thank you. Okay, thanks again, especially invitation from Primala. Thank you very much. When you approach through the Professor Janab, I was a little bit having different opinion because basically my talk is purely mathematics, but your conference is mixed mode basically. But never mind when I say, then you said, okay, welcome. So now I'm here. Thank you very much giving me this chance to share my talk and my basically opinion about the topics on the generalized functions and the singular operations. Yes, I am from University Putra Malaysia, and recently our department has changed from Department of Mathematics and including the statistic as well. Actually, we used to have statistic as in the department, but was not in the basically name as a Department of Mathematics and Statistics. Okay, thank you very much again. Now we can talk about it. I'm not sure whether anyone have heard about the generalized functions or sometimes the distributions. But when we say distribution, most of the time, the idea of the statistical distribution is coming out. But the statistical distributions is also inside the generalized functions. We can consider them as a particular group of the or space of the functions. So what is this one actually? It will generalize the classical functions and allow, what is the meaning that classical function cannot do that? For example, every derivative is continuous in the classical sense, but not every continuous is differentiable. So is it possible to make this one is equivalent or every member having the same continuity and the differentiability at the same time? Second, I will say like this, distribution theory in its full scope is not easy basically. Also, I cannot summarize here, sorry, everything maybe requires 1 semester or maybe 2 semesters of the class work in the sophisticated manner. Never mind, we will do so now, but at the same time, have many applications in the several fields, especially in the science and engineering, where non-continuous phenomena naturally lead to the differential equations, but whose solutions are not classical functions. We will see some examples in the future, in coming non-continuous phenomena, but solutions are not classical. So delta distribution, for example, therefore, play a particular role in the development of the operational calculus that we can try to think about it. And in order to investigate the properties of the ordinary differential equations, as well as the partial differential equations, through their fundamental solutions. I think when I say fundamental solutions, you are familiar with that one as well. Okay, never mind, let's go. So what we will do basically in here, we will try to give some singular operations, generalize the functions and their applications, if possible, with the variable coefficients, not the constant coefficients only. Now I will give you one dedication from the Sir Lytle, and he said to the Paul Dirac, who saw that it must be true. Then Lawrence Schwartz, I am not sure whether you have heard about him, and who proved it. And George Temple, who showed how simple it could be. So this is basically development from Paul Dirac. As you know, Paul Dirac is the Nobel Prize winner. Lawrence Schwartz is the basically field medalist in the area. Okay, never mind. Therefore, the concept will be Dirac delta functions and their basically derivatives, linear functionals, and delta function in the convolutions. As you know, they will act as a particular identity in the convolutional sense and the singular operations. Is that clear, my voice so far?
Yes, sir.
Okay, thank you. Now, when we look at the origin of the delta function, even though it's named as the Dirac delta function, but actually in the literature, we can see some study or work on delta functions. Of course, they don't say at that time exactly delta function or Dirac function, but when we look at the Kirchhoff electromagnetic theory, he defined a function in this way. As you can see here is the limit, and the right-hand side is the look like the Gaussian kernel, basically. Then we look at this and take the limit, we will see, this is the reference to the Kirchhoff, if anybody interested, then we can see that this limit is equal to the 0, wherever x is not 0. 0, wherever x is not 0, at particular point x0 is infinity. Is like this, delta behaving this way. Then after that, when we look at the integral, and taking from the negative infinity to, then you will see that it looks like the probability density function, which is 1. Which is 1 when x is positive, 0 when x is 0 or negative, sorry. So now we can, when we look at this way, we say that delta is not a classical function in the mathematical sense, but Kirchhoff referred to that one as a unit impulse in the electromagnetic theory. So now we will continue from this point actually. So Dirac delta function is not a function in the mathematical sense, rather it is known as generalized functions on the real line. And it is 0 everywhere except at 0. At the same time, total integral is over the real line is 1. So because of this property, you can start working with the statistical side or probability side as well. But we are not going that way. Okay, then delta function only makes sense as a mathematical object or as an operator when it appears inside an integral. Because outside integral, infinity, you cannot do any much actually, not that much actually with that idea, because 0 everywhere and only 0 is infinity. So thus formally defined as a distribution or generalized functions, or also sometimes we call as a measure as well. Applications ranges from engineering to the finance and many more actually coming out every day. Now later mathematical community call it distribution or generalized function and start working on those type of functions and their properties together. Later on, we will see limiting process is the best actually to represent the Dirac delta type functions. But at the same time, they have some integral expressions. For example, when we put anything around there, then translation will be FA, as long as f function is defined at particular point A. Or total again is the 1, or you can take particular A, if A is 0, for example, is the F0 value for any case. But now question is coming here. If F0 is not defined, what will happen then? When you put there some function, for example, 1 over x times delta or Dirac delta function is inside the integral, is not defined. So what you can do, or logarithmic functions, or any asymptotic behavior that you can put in there. So at that time, at the particular point, that asymptotic behavior basically is not recognized by the Dirac delta function. So you need to make further interpretation or assumptions. I will talk about just little about the Dirac Dirac from England and passed away in Florida, studied electrical engineering at the University of Bristol, and later on moved to the College Cambridge, John's College Cambridge, and he has first major contribution in the quantum theory. Because of that, he got the Nobel Prize in the 1933. And this is his reference to do. You can, I'm sure somebody heard about this quantum mechanics, especially recently with the quantum computing. When we look at the work of the Dirac, we see only this much, not that particular information that he provide. Just only he provide very general. This is again one, and this is further in the Dirac work. Delta represent the unit point charge at the origin, and derivative. Dirac treated the derivative of the Dirac delta function or delta function as the dipole of the unit electric moment, since because you can see the first moment of the derivative is -1. Because of this, he has treated this one as a dipole of the unit electric moment. Then, of course, in the scientific area or research, there are higher moments of the delta R 0 all the time that we will see after a while. Okay, now, but higher derivatives of the delta, not I am talking about the higher derivative of the moment or higher moments of the Dirac, but I am talking about the higher derivatives of delta function represent the more complicated multiple layers in the scientific area and has physical and engineering applications. And if anybody wants to see the reference to do that, you can see it, Hoskins, for example, distribution, ultra distribution, and other generalized functions related to this. So therefore now we can say that as a conclusion from this simple website, for the physicist, delta function is well designed to represent the charge density of the point particle. But for the mathematics, it will take some time to develop the full theory actually. Okay, these are the things you can see in the, again, Dirac work. I'm not going to talk about that much. Only I will say here is symmetric respect to the, you can see negative x and the x. So Dirac delta function or this type of function, they are symmetric functions. And you can see at the same time the other properties as well. The moment, again, here, you can see all the moment of the Dirac delta or higher is 0, except its derivative 1. Derivative is the, that we have, say, unit pole. Okay, then after that, to talk and work with the delta like that, infinity at one particular point is very difficult. We cannot see that much information inside that definition. So Temple got the idea to work with the sequences which converge to the Dirac delta. So before reach to the limit delta function, we can, with this way, we will be able to look at the behavior of the functions actually or sequences. But this kind of sequence has some properties. For example, we call them as a delta sequence for the ordinary function converge to the Dirac delta function or singular distributions, and which is always positive on the above the x0 line and continuous and integrable or summable over the real line and is equal to the 1. And at the same time, if you look at this limit, negative infinity to negative epsilon, from epsilon to the infinity is equal to the 0. The sequences satisfying this kind of properties. After that, now, reference to that one, you can try to see Theory of the Generalized Functions by the George Temple. Then, when we look at this way now, we will be able to work with the delta function before or reach to the Dirac delta type by taking the, for example, the ordinary sequences and develop from there by satisfying those or conditions, make them regular. They are regular, but converge to the singular Dirac delta. But here, Dirac delta cannot act on its own way, always acting with some kind of test functions that I will mention as a infinitely differentiable functions having the compact support. And when we look at this, then we will be able to see, for example, among them, you can see the Gaussian probability density satisfied that rule actually. One choice is like this. Another one, is that only one? Of course not. We can have several actually. Another one, for example, here you can see another one is epsilon over x squared plus epsilon squared, which is again, you can play this one as a 1 over n and goes to the infinity, and you can have it again Dirac delta approach or tends to Dirac delta. More examples you can generate, and when we look at the literature, we will be actually able to see these common limits of the Gaussian or Lorentzian or Dirichlet kernels. They are act as the regular sequences converge to the Dirac delta or delta function. Okay, so far, so now we can say that many of them, many limit forms that produce the same generalized functions, we call them equivalent. Later on, we will see what does it mean, this equivalent, meaning that. In other words, when you process Gaussian, maybe at the end, it will act as a Lorentzian, or maybe Lorentzian will act as a Gaussian or as a Dirichlet, and so on. So the picture of the delta is like this. This is, you can see from the bell kernel or bell curve or Gaussian kernel, basically like this. And the derivative of the delta, you can see like this. When we try to differentiate delta function, we will have like this. But these are important matters in the impulse contributions or in the impulse level. So in other words, changes happen in the very, very short time or short period of time. You can see here, big changes happening in the impulse case, very short period of the time. Or you can consider that one is here, very small area, T0 minus T tau and the T0 plus tau, very small tau, of course, small number, or look like the epsilon. Okay, now, further, even though I have mentioned, what is the reason, what we can do for these kind of things, or why do we study this distribution theory, basically? What is our motivation to? Then first is this, as I mentioned, differentiable equivalent to the continuity in the differentiable function space or generalized function space. This is the first one. Second one, as we know, in the classical sense, if the limit exists, for example, like this, Fn is the sequences and some function around there exists for all nice test functions, then we cannot say in the Riemann sense, this sequence limit exists in the generalized function, only available in the generalized function, not in the Riemann sense. I mean, this limit does not bring in the classical sense limit of to this sequence, even though altogether exists for every nice functions phi. Or some further, for example, you can have not only problematic like that, but non-differentiable functions having the corner. They are problematic ones, or having cusp, similar, or having vertical tangent, for example. If you try to differentiate this one, will go to the infinity. Then you cannot have it easily. Or discontinuous functions. Then you will be able to handle all these type of functions with the generalized function idea. Actually, if you look at the Takagi function, you can try to handle step by step in the following way. Or as you know, you have in the literature one very, very strange function, nowhere differentiable function, for example, even though they are continuous, but nowhere differentiable. For example, Weierstrass, the function is like that, but they have application in the, for example, nicely in the finance. So you cannot leave it like that. So we need to work further. Continuous, nowhere differentiable functions are typical type of the Banach space of the continuous functions. So therefore, now you can use that idea and to work out. And they are the class of the CAB, actually. Okay, never mind. So now in the area, there are some basically available literature. Maybe somebody interested can look at this continuous nowhere differentiable functions. And actually, somebody say that they are monster of the analysis. You can see here, monster of the analysis. They are not easy to handle in the classical analysis. That's why. And only not like that, but at the same time, when we look at that pathological functions, they are very important in the applications. For example, fractals is coming from them. Chaotic behavior coming from them. Wavelet idea coming from them. Mandelbrot fractals is coming from them, and so on. Yes, they are basically at the junction and making the huge contribution in the development of the mathematics or applied mathematics. Okay, on the other side, have a look at in the history who are using. For example, when we look at the Hadamard using that idea, and Sobolev was also applying the idea to do partial differential equation theory as well. Okay, but Hadamard or Sobolev or until the Schwarz, basically, the theory was not settled properly. So Schwarz basically contribute and won or gained the field medals in the area for systematic treatment or contribution. What is the problem actually? Why is like this then? Then because generalized functions, they are not easily multiplied, for example, or you cannot easily get the convolution, for example. I mean, both of them, if it is generalized functions, you cannot easily multiply. We will see later on. Okay, so there are applications in the engineering. For example, in the quantum, that delta square is very much applied. So delta times delta is delta square, but what is it, that one? How we can formalize it? So Laurent Schwarz formalized that one and got the field medal because of his contribution in the area. So therefore, now I will say this remark: theory of the distributions is a linear theory. We can extend some operations which are valid for ordinary functions, such as these operations, for example, addition, multiplication by scalar. Addition, multiplication by scalar. We call them regular operations. Other operations can be defined only for particular class of distribution or particular class of general. We call them irregular operations or singular operations. For example, multiplication or product of distributions, convolutions, convolution product, composition of the distributions. For example, FOF, FOG. For example, what is the meaning in the generalized function theory? And also ultra distribution theory as well. In other words, upper class of the Fourier transforms. We call them, when you work, their member is the generalized function. We call them ultra distributions. So these are the area where it is still not settled. So when we look at, for example, Heaviside function times delta is well known in the quantum. or x power negative 1 times Dirac delta is well known in the quantum again, or delta prime times delta is well known again. So these are actually special interest to the physicist or physics and widely used in the quantum theory. Similar, you will have further like this, for example. Now, since the h of the fractional derivative, whether we can replace those things, for example, with the derivative, but fractional one, then fractional one, fractional derivative, and another fractional derivative. Not necessarily they are same level or same order, or others you can see. For example, one of the research that I have done when I was doing my PhD time, it was this kind of things to try to handle these logarithmic singularities, for example, with the Dirac delta and the more general form like this. So therefore, still area is hot area, but we cannot make maybe that much contribution in the area. Of course, development is very slow. But what we can do, we can continue making how to generate the regular sequences by using the infinitely differentiable functions. Just now I have mentioned in the previous slides how to generate the regular. Now we will try to make a little bit more further, use this kind of information. I mean the function satisfying this. Now we add here, you can see is symmetry as well. Positive, again same. For outside is 0, is the same. And the total integral is also same as well. But now we add the symmetry as well, symmetry conditions. By doing this, now we can generate any way is the regular sequences. In other words, these regular sequences converge to the Dirac delta, but they will act as an identity for the convolutions when we look at it. So now the idea here, when f is singular, we try to use the convolution with the regular and infinitely differentiable functions. We try to remove the singularity if possible. This is the way and the idea. Regularize the singularity. So therefore now, instead of working f, I can work with the sequences this way. And this is the basically linear form we can use. So then this Fn is a regular sequence, infinitely differentiable, and converging to do at the same time f as well. So now this is the way to regularize the singularity. Then you can look at now, if f and g distributions, you can make the fn and the gn generate like this. Then later on, try to multiply or try to convolute or try to composite them, combine them together, and so on. Anyway, I will omit this one later on, come back maybe. Now, what will happen now if we consider those sequences but fractional order derivatives or fractional format? Is it possible? So what shall we do? Is there any interpretation for that? Still question is open. We can try to basically go further research on that area. I'm going to omit this support. And now just I want to give it this implications. Sorry, just a moment, please. So this is the basically infinity differentiable and m times differentiable and m plus, sorry, c2 times differentiable and c1 differentiable and so on. This is the basically implication among the infinity differentiable functions and the continuous functions or differentiable functions basically is like this. Anyway, then after that, we combine them now. If the phi be infinity differentiable functions having the compact support, we call them test functions and combine all together, bring them as a D. D is the space of the infinitely differentiable functions with compact support. We name them test function space. test function space because they are going to act on the distributions. Distribution has no point-wise character. They always together with the some test functions. Then, but there are some comment that I want to say. For example, if f is in the D, then meaning that derivative of the phi in every order or arbitrary order is in there, but the integral not necessary. When you look at the then integral of to that infinitely differentiable function is not necessarily in the D space because you might break the support idea, compactness of the support at that time. Maybe they will not have the compact support. Okay, never mind. But what we can do, we can try to manipulate them and work with the subspaces. For example, instead of that, you can generate the phi 0 in the following way. Then after that, your phi 0 will be infinitely differentiable in the subspace as well. And then since you generate the space, of course, you can talk about the topology and the convergence on that one, but I am not going to. Actually, you can define the convergence in the following way. Every order of the derivative will go to the 0 if n or as n tends to infinity. So we call that one is derivatives tend to uniformly to 0. Okay, now we combine them as a linear functional together with the test functions, and we will have the linear functional acting on the test function in the following way. Detail you can see at the time, Schwartz. It will be like this. Okay, let me show you this way, for example. Now, if we able to define this way, then we call them the prime or space of the functional, linear functional, and we name them set of the distributions or space of the distributions. Of course, it is a vector space, and the topological character you can define similar to the D or test functions space as well. So now we can say a linear functional you can see here, define as an integral, and since the support of the test function is bounded or compact, basically, it will be like this. Then we say this linear functional is continuous on the D. On the D, you can see test functions and smooth compact functions and known as the generalized functions, but they are not the classical functions. Now, is there any similar way in the literature? Yes, I can try to relate, for example, this linear functional. Now, everybody is familiar with this kind of integral, having the kernel, and the next to that one, there is some functions. This kind of things is available in the literature. So now, your actually linear functional is very similar. If you pick up the test function as a kernel, of course, maybe with little arrangement, then it will act as a kernel, basically, or as a test function, basically. Or like, for example, here, you can see Laplace transform is very much, you can see here, is very much related with the test functions. You can consider that one. Or maybe further, you can consider like this, the integral transforms. Basically, since this one is the kernel, you can consider your kernel as the test functions. Of course, with the little, again, arrangement in the compact site or the domain, basically. Or you can have the other, for example, kernels. You can have the Henkel transform having the similar kernel, okay? Or maybe you can have the Hilbert transform with the similar kernel, as long as integral exists, of course. Yeah. Then every summable functions, when we look at every continuous functions is summable on the bounded domain. So therefore it is a linear functional, and therefore it is a distributions. So you can see here integrable or summable function space. L1 is subset of this distribution space. Actually, you will have this implication among all these things. You can see here, this is the set of the test functions with the compact support, LP spaces, and L2 Hilbert spaces, L1 Banach spaces, and this is the generalized function space or Schwartz space, and so on. Now, another one is that interesting property here, we can say the test function space is dense in the prime or distribution space. So what does it mean now? You can see that all these actually function spaces, L1, L2, LP, they are dense in the generalized functions as well. Of course, the detail we can start talking about, but I'm not going to. Then the first thing is coming derivative. What will happen if we try to define the derivative of this kind of linear functional? Then when we look at it by using this simple integration by parts, and you can use the property of the test function, support is bounded or compact, then you will see that this is the way now. What is the benefit of this? What is the benefit of this? For example, if the F is having the singularity, you can try to work with the prime of the test function at that time. So it will be same exactly or equivalent. For general case, of course, the new one is also, derivative of the F is F prime is a distribution again. Or general one is like this. Somebody can use the induction method and try to prove this way. And derivative also is a distributions. Then look at now very strange things happening now. Here, when we look at this simple function is given as x and 0. If x is less than 0, 0, greater than is x, is the locally summable function. And its derivative, when you try to differentiate this function now, acting as a Heaviside function. And it is the basically well-known Heaviside function, which is locally summable as well. But when we go further, one more level of the derivative of the Heaviside, or second derivative of this locally summable function, we reach to do basically Dirac delta type functions as well. This is the functional side, generate the Dirac delta by using the locally summable functions. In other words, you can see Dirac delta is actually second derivative of the locally summable function. Okay, the general case, you can look at it here. I'm not going to go that much, already so much time. Now I want to ask a question. You can think about it. What will happen if we try to think about, instead of the Dirac delta, but what will happen fractional delta in the linear functional form? In other words, what will happen here? It's in the distribution sense. Whether we can generalize this for the every test functions and for the fractional order derivatives. But for this, I want to say now, have a look at, for example, approximation of the delta. How we approach to the delta by using the approximation or limiting process. For example, this is the now limit. And as you can see, taking the limit, you can see the Dirac delta. This is the Gaussian kernel, basically. But when you try to take the derivative of, again, taking the limit and approach to the classical prime as well. And further, you can do second derivative, third derivative, and so on. This is the approximation to the Dirac delta by using those well-known kernels or regular sequences. Maybe general, more general case for any n, it is like this. But this is classical one so far. Now, fractional one, what will happen now? If we try to take the derivative of the Gaussian kernel, for example, with the fractional order, then we will see that the result is not going to come out as classical one. It will involve with the hypergeometric functions. For example, we can try to see this particular one. Maybe this one is very simple, but meaning that there are some representation of the hypergeometric functions in the form of this way. Or maybe further, you can look at it not necessarily 1/2 order, but any order you can see here, and it will be in the geometric form as well. So this one, hypergeometric form. This question marks depends on your order. Depends on your order. Not depends on your n, okay? But when we look at it for particular case, for example, we will see that if the half, this is the way now. Now, meaning that this one at the same time is very equivalent to the representation in the classical sense 1/2 d prime, actually, since it is 1/2. So somebody can try to show this one, actually, this representation, how approach to that one. Or if you take the order negative, which is considered as the integral, then you will see the, again, hypergeometric. Now you can see here now, look at the parameters inside the bracket here, square brackets, change completely now, this one as well. Of course, order also change as well here. So now, when we look at here, this is the hypergeometric function, actually polynomial forms 2/2 or f(2)(2). So this is the case happening with the fractional order. But I have a command during that time, okay? For example, what will happen, this in the, I'm sorry, just a moment. What will happen this one in the convolution? Remember, we used to generate the regular sequences by using the singular functions or asymptotic functions. Are they going to play the same role as the direct function, ordinary, maksud, or meaning identity roles in the convolutions? So now we can say, how about the fractional order, whether we need the extra interpretation, whether they are equal to the directly? No, not necessarily like this. Actually, we have some examples, they are coming out different. For example, even when you consider the just only half, they are not anymore same. Okay, they are not going to approach to the f directly, taking the limit like this, unless very particular forms. So in other words, we can say that the 1/2 fractional order may not even have support as a finite interval. So therefore, we need some interpretation on that issue. In other words, the fractional order not necessarily keep the compact support that its derivative in the fractional one is going to have again compact as well. No, not necessarily. You can check it. And so therefore now, for general case, whether we will have this one for any test functions for any ordinary, the fractional order. Now when we look at back, the simple absolute value function, this is the one, is not defined. I mean, f prime is not defined at the particular one point only. But now we can interpret and use the derivative idea as a signum functions. Okay, first derivative is the sine function at that time. But in the classical sense, does not have derivative in the normal limit. But we call this one is weak limit or weak derivative or as a distributions. So this is the way to cover those corner-like functions. But on the other side, the distribution theory having enough problem itself that I have mentioned. For example, problem of the multiplication or problem of the convolution or problem of the composition and so on. Have a look at this simple result. For example, one side is 0, another side is when you combine together, composition basically is not commutative. You can see here. Or you can also say that is not associative actually operator when you look at the last one. The detail you can see from those, for example, so many people, they are trying to contribute in the area, and they try to generalize the definitions and try to put some more and more and more some functions in their spaces. That's why they try to generalize by saying that new generalized functions, and in that particular, still particular, but more general than the others, and the multiplication will be available. Or other people you can see in the literature, they have worked out with the many different ways. Okay, how about non-differentiable function in the classical sense? Having corner, but their fractional order. Surprising, they are singular, or they are not basically having prime, ordinary prime or derivative, but their fractional order exists. Fractional derivative exists. Okay, but we define them as a distribution again, their fractional order. And therefore now we can try to summarize the question or fractional order. This one, derivative, fractional order, and f, of course, is the linear functional or integral, at the same time fractional integral. What will happen? Or the other you can see here, for example, or some integral transform in the form of Mellin transform, Fourier transform, or so on. Or in other words, we are trying to say what is happening now if we try to take the fractional order derivative for the linear functional actually. Okay, whether you can apply direct derivative definitions, or we need to make some modification or some assumption or arrangement. So far in this area, for example, one of our work to graduate Kronecker operational matrices, we apply to do matrices, this kind of idea with the fractional calculus and some applications. What we have done in there, basically we apply to do operational matrix for integration and the differentiation, and we introduce the Kronecker convolution product and expand it to do Riemann-Liouville fractional integral of matrices. In this direction, I can list this one, or we also work for the Mellin transform, fractional Mellin transform as well. And we have applied this idea to do some more applied case application in the option pricing, for example. You can look at the literature for this kind of publications. And also we have later on, we extend this idea to do weighted geometric functions when the Prof. Agarwal visit our department, and the fractional derivative. And at that time, we introduced some weighted hypergeometric functions and generalization of two, and suitable for the generalization of two Caputo type fractional derivatives. Okay, some more very recently, for example, some application in the generalized fractional operators in the analytic function spaces that we have worked out with, again, in other postgraduate students, and it is published in there. And what we do in there, we define the new generalized integral and the differential operators with two parameters, type of the fractional. At the same time, you can see two parameters having the fractional inside the operator. Then we investigate some of the geometric character and boundedness properties and so on, and also their relationship with the hypergeometric functions as well. So these are the so far. And the one current going on one study is, now we want to apply this idea to do fractional partial differential equations for the stable Levy process or Levy stable process. In other words, it is very much applied. It is being considered for the time fractional Levy diffusion equation for the exponential option pricing model for the European option pricing with the risk neutral parameters. Okay, one more, I can say like this, for example, a new class of two summation formulas for the generalized hypergeometric functions. with this study, actually, we can look at the opposite way. By looking at the generalized hypergeometric functions, we can look at, lead to the study, the detail on the representation of the distribution or generalized functions, rather than this way, the summation formula generalize the hypergeometric function. But now, with the hypergeometric functions, whether we can reach to some good result in the distribution theory or generalized functions. Okay, when we look at the simple one, when consider one again now, family of the smooth functions, then you can consider this one, and this is having this shape that I will show you just now. Okay, when we look at the limit, it will be like this now, for the limit of that when we try to plot the graph of that simple one. But when we increase the number of the iteration, look at now, when we look at now, each time you can see compact support is getting smaller and smaller and getting sharper and sharper. Actually, as if from smooth study will go to basically you can see singular corners or having the corner in the pictures. And when you increase the iteration, it will be more and more. You can see here as a one straight line, vertical line. This is the characteristic of basically some kernels, but acting as the Dirac delta distribution as well. Or maybe more, you can see now almost basically vertical line, 100% almost. Okay, now what is happening here actually? From one kernel type, by taking the limit process, as if changing its structure, going to another type of the kernels. And we can maybe study a little bit more detail on these issues, how to convert from one to another. That's why I mentioned that it is equivalent kernels. But when you look at back, again, simple one, then you will see that is the derivative of h, because you can consider at that time this behavior. Now have a look at this behavior. Actually is 0 everywhere. You can come back, and one after that it is going to be look like the Heaviside functions, and derivative is the Dirac delta as well. So with this approach, we can easily now say that the dn tends to 0 everywhere, very also fast as well, very fast as well. Okay, now you can change your kernel or your function, but you will have the approximate again Dirac delta as well. You can approximate the Dirac delta with the several different types as well. Now I can say now basically this, and since fractional derivative of two functions are usually no longer elementary functions, we have seen even the Gaussian kernel will generate the hypergeometric functions, fractional. So therefore, their properties are more complicated than those integer orders. Okay, I will just, so therefore now, try to ask the same question again, whether we can generalize this fractional, linear, functional idea to the whole functional. And just look at now fractional derivatives. Now it will be like this. Of course, sorry. It is more complex. You can see okay, maybe later on we can study some more actually. Again, some more. Now I am coming back to the same questions, whether we can substitute Dirac delta derivative type in the quantum theory, and what will be the effect of it. And whether similar things you can apply, for example, okay, this, and you can see again the differences between. This is typical, okay, example as well. How about the differential equation theory? Whether all these things nonsense or they have some application in the differential equation side. When we look at the literature, for example, I can give you the Canval Generalized Function Theory, the book. Then he summarized the cases. Basically, if we have the operators, differential operator or differential equations, whether solution is smooth enough in the classical sense, or solution not smooth, but acting as a satisfying the distributions, or maybe solution is totally singular as a distribution solution as well. So now, when we try to put the right-hand side as a singular, then we cannot do numerical that much work, because not easily integrable or summable. Then, but we can try to apply the distribution theory at that time. For example, if you have the simple initial value problem, very simple actually, look at this operator on the left-hand side. Then right-hand side, this type of functions you can have all the time in the Fourier analysis, for example. Then solution will be this. Basically, it is not the serial solutions. It is, you can see here, is the distribution solution. In other words, not the classical solutions. Or we can try to figure out like this. If we have some operator, or maybe instead of operator, you can consider the linear functional. And when you have the x, for example, as that one, what will happen? This one has no meaning now in the ordinary sense, because if x goes to the 0, then it will be infinity over 0. Is not defined properly. Or maybe more general case, you can have it right-hand side maybe more involved with the either fractional or maybe ordinary derivatives. And this type of solution, if it exists, we call them fundamental solutions. Now, in the literature, with the work of the Brian Fisher or Temple and the others, they try to give the solution to this type of by regularizing the singularity, but it's coming from here, which one to regularize, first one or second one, or both of them, and so on. When we have, for example, single regularization, either first one or second one, the result is coming out different. Therefore, we call them non-commutative. But when you try to regularize both of them, at that time is the result is the commutative. But needs lots and lots work at that time. We try to give in the other one, if you have the one simple differential equation in the following form, how to solve this kind of things. We try to give the partial solution for this and multiply together with the ln p x and this type, but in the distributional sense again. Is not the classical sense, because the ln 0 is negative infinity. So negative infinity times infinity is not defined, multiply by. Okay, but the coefficients are in this form. Maybe we can try to identify some functions. It will work for a particular one, and it is published in this way. By the way, Brian Fisher was my postgraduate supervisor when I was doing my PhD. And at the same time, what will happen, the role in the exchange formula? As you know, this is the exchange formula for the Fourier transform. In other words, Fourier transform will convolute the two functions as a ordinary multiplications in the Fourier transform sense as well. This convolution exists in the Gelfand and Shilov sense as long as f or g has bounded support, either of it, okay, or supports of the f and the g are bounded on the same side. At that time, you will generate the new type of the sequences converge to the Dirac delta functions image under the Fourier transform, and they will act as at that time convolution identities. Okay, and you can look at this Trev's work, but now whether we can try to substitute that one by using the again fractional regularization as well in the ultra distribution spaces. This one is open question, is not properly done yet. I think so far, okay, these are the things that I want to mention. And you can just, sorry. I have just only one more things. By combining the two non-commutative, and taking the average of them, you will have the commutative new definition or multiplication for the distribution and the ultra distribution as well. But my concern, whether we can replace these delta sequences in the fractional form as well, and whether still we can do this multiplication. Okay, I will stop here and I will say thank you very much for your attention.
Thank you, Professor.
Welcome.
Dear participants, any queries you can ask the resource person. Any questions can be put either in chat box, or you can unmute yourself and you can ask the resource person.
Okay, no problem. I will try to. Just a moment, please. Sorry, give me the 1 minute, please. Just let me. Okay. I think, remove the presentation. I will post my PowerPoint to Prof. Pirimala, then she can share later on. Okay, anything else? Any question more? Welcome everybody. I hope you understand the matters that we have discussed here.
Thank you very much for a wonderful session, sir.
Welcome.
The topics you presented will surely be helpful for the aspiring researchers on this particular domain. Thank you for sharing your research ideas.
Sorry, just let me interrupt. There are so many open questions, okay, if you listen carefully.
Yes, sir.
Yeah.
Thank you, everyone. We kindly ask the participants to leave for a tea break and assemble back here at 11:20 sharply. Next, we'll have the session taken by Dr. Mohammed Sajid, sir, on the topic fractals.